All right. Okay. To help address some points that we did not get to on Friday, such as when are we doing a two-sided test versus a one-sided test? And what that's going to affect is at the end, either if you use table A, which as I said is not necessarily the best idea, considering what we're going to do in a later chapter, but if you're going to use that, or if you're going to use normal CDF on the calculator, or if we're reading probabilities from the bottom of table C, whether we have a one-sided or two-sided test is going to affect what we're doing at the very end with what we get for probability or p-value. And we'll address a few other things as well. Like, for example, the one we had on Friday, we rejected. No, we failed to reject the null hypothesis, correct? Because we had a probability that was pretty high. Bigger than output, correct? Okay, so when do we wind up rejecting the null hypothesis? So, for what I hope is simplicity's sake, it makes things easier on me, we're going to refer to that same data that we had from the end of class Wednesday and that we were using throughout on Friday. So if I remember right, we had the sample of 18 newts, and we found that the sample mean, X bar, that was 25 point, a bunch of 5s repeating, and then a 6, correct? Does that ring a bell from the notes? Okay. So after the decimal point, I think we had 7 more 5s. Well, actually, let's see. This would be 6 more. It was 7, you're right. Okay? Does anybody remember, or can you see it in your notes right away, what sigma was? Sigma was 8. Okay? And at the very beginning of Friday, we came up with a 95% confidence interval. If I remember correctly, we rounded at the end to the nearest tenth, and I think we came up with 21.9 as the lower bound, and 29.3 is the upper bound. Is that correct? Okay. All right. So then when we turned it over to the material in chapter 15, we were testing whether the mean in the population was 24 against an alternate hypothesis that it was not 24. And again, that's a two-sided test, because we're not saying that mu is less than 24 or mu is greater than 24. We're just picking that it's not different. We haven't picked which side of 24 it's supposed to be on. So one thing I want to warn you about. In your null and alternate hypothesis, it's all about mu. Think about that really annoying Megan Trainor song. All about that base. The hypotheses are all about mu. Nothing about X bar ever is written in the hypotheses. Not the symbol X bar and not the numbers that are related to the X bar. Okay? It's showing up, or is it getting cut off by the screen when I write two-sided? So two-sided. Alright, what significance level did we set? What was alpha? 5%. And we had talked about how the 24, yes, I was picking a number kind of out of the air, but it was in between the lower and upper bound. And on the other hand, 95% and 5% add up to 100%. It's almost like we're doing complementary things. Without repeating everything we did, I want to show you on this one how we could use normal CDF to get a probability to then compare against 5%. So if you're claiming that the population mean, mu, is 24, the 25 point, bunch of repeating fives, and then the 6 is above that. We want to find out, is it far enough above it that it's an extreme score so that it would have a low probability of occurring. So low that it'd be less than or equal to alpha. And we use table C. I'll be showing more with table C today as well, but we use table C Friday to get a range of values that P could be between. If we use normal CDF, well, it's a two-sided test. If we're going to reject the null hypothesis, it would have to be so far up there that we have that total of 5%, 2.5% on either side. So to see if we've got something less than or equal to 5%, we already know what happened from Friday, but just to see how we can do that another way, let's tilt it this way now. Since it's a two-sided test, we're going to double normal CDF. And by the way, when I've written write the complete command, I mean after you, for those newer calculators, after you have typed it in and press paste, how does it show it in the home screen? That's how I've been writing that. Your last two, based on the stuff from chapter 11, are going to be mu, which we claim is 24, and then the standard deviation, not of the population, but the sampling distribution of X bar. So whether we do it this way or whether you use the formula that I showed on Friday, what is our standard deviation to put? Not 8, but what? Eight over, where is 18? Okay? As for figuring out what to put for the first two, your lower and upper bound. If my X bar was less than my claimed mu, I would go from negative 10 to the 99 up to my X bar. Since instead I have X bar bigger than the claimed mu, I'll go from the X bar up to 10 to the 99, positive 10 to the 99. I'll actually type the whole thing when I put it in the calculator. Since we already know what that number is, I just didn't want to write it all again on the board. Okay, and we can aim it at the screen now. Hopefully it's capturing the calculator a little better today. So 25.555555556. Upper bound is 10 to the 99. Mu is our claimed mu of 24. And sigma, 8 over square root of 18. Is there a question before I hit enter? Okay, so paste it in, or for those of you with the older operating system, it would look like what I have in the home screen right there anyway, which is what I was writing on the side. Just like in chapter 3 and chapter 11, we would round that to 4 places, since that's about the furthest we've ever seen a probability written as a decimal. So that's going to be about 0.4094. Or 40.94%. What we did on Wednesday, because it's a two-sided test, 2 tails. Okay? Now on Wednesday, we got our z-score. It's our test statistic. And we compared it to the z-stars here towards the bottom of table C. Then we found the 2 closest in that case, tracked them down below that to the 2-sided p-row. What were the 2 values that we had on either side of p? See, this is a more exact value for p. Still an approximation. The calculator was already rounded before I rounded to 4 places, but it's more exact. What did we have from the table instead? Where were we? Okay, so we must have had a z-score that was between 0.674 and 0.841, right? Okay, that's giving us probabilities that are very high. This is between that. It's just more exact than what we can get from table C. The fact is, though, that is bigger than alpha. So just like I said on Friday, whenever p is greater than alpha, you fail to reject the null hypothesis. Really, I made a comparison to a court case, but I never say I have proved or disproved the null hypothesis, or that I've proved or disproved the alternate hypothesis. I can just tell you what evidence has been brought, either in favor of rejecting or failing to reject the null hypothesis. Failing to reject would be saying innocent, even if we don't really know 100% that it's innocent. And rejecting it would be to say that it's guilty, which again, you don't ever really know 100% that it's guilty. So interpreting this, by failing to reject, we do not have enough evidence to say that the null hypothesis is wrong. We don't have enough evidence to say that the mean healing rate is different from 24 micrometers per hour. We do not have enough evidence to say that it is different. So we're going to stick with this, unless we get some other evidence that will eventually outweigh it. But as from this sample, not enough evidence. Questions? All right, let's change 2 things. And through this next change, we'll both do it the long way, calculating Z and looking stuff up in table C. And we'll do binomial CBS as well. We're getting equivalent information. So what if, actually, let me ask you a question. No, it's for the next one. What if instead of 24, what if I thought it might be 22? I wouldn't come up with that out of the air if I was really researching this stuff. But let's say someone thinks they have reason to believe it's 22 instead of 24. They'll go do the same experiment. Let's say they use 18 newts as well. Population standard deviation is still 8. Let's say that their sample comes up with the same X bar. Let's use the same level of alpha, 5%. We need 5% or less to say that, if that's our probability, then we would reject, and we would think that it would be different from 22. Okay, so if we're doing it the long way, we have to calculate Z. X bar minus what? Oh, sigma shows up as part of the denominator. Mu, in fact, the mu naught, the mu in the null hypothesis. Okay, what's sigma divided by? And just like we had over there, and just like we had in confidence intervals. Okay, so we're putting in the 25 point bunches of 5s. Minus the 22 that we're claiming now. Over 8 divided by square root of 18. And I know if I subtract 22 from that in the numerator, that's going to be 3 point something. So 3.555, 5555, 6. Remember, when we're dividing by the fraction inside the fraction, we put parentheses around that. So parentheses around 8 divided by square root of 18. I believe that this is going to give us a bigger Z-score than what we came up with in Friday's example. Where did I say to round to when using table C? Based on the Z stars that are written there. 2 places, 3 places. Z stars are written in 3 places. So we will round that to approximately 1.886. Because of the time we had available on Friday, I didn't give you the full story here. What if we had come up with a Z star that was smaller than even 0.674? What's happening to either the one-sided p's or the two-sided p's as z's get smaller? As z gets smaller, what happens to any of these p-values, either in the one-sided p row or in the two-sided p row? They get larger. Go the other direction, as z gets bigger, look at either row, the probabilities, the p-values get smaller. So what's that say? If we had if you look up here for a moment, let's say you had a z-score of 0.4, even less than this. You couldn't trap it between 2 values like we did on Friday. You could only compare it to one closest thing. 0.4 less than this. Then if we were doing a two-sided test, we'd say our probability is bigger than 50%. It's a one-sided test, bigger than 25%. On the other hand, all right, this got cut off here, but let's say we get 4. Definitely bigger than the Z star listed here. With a one-sided test, then, we would have a probability that is smaller than 0.0005. You'll notice the direction I had with the inequality over there versus over here. Smaller Z star, bigger than the probability listed. Larger Z star, smaller than the probabilities listed. You'd have something really extreme. You were doing it the longer way, you had something like a 4 in something we were doing related to chapter 3 or chapter 11. Do you remember that? Well, we wound up saying that, well, it's past the stuff that's on table A, that if it were talking about less than that, its probability is virtually 100%. So something similar here. I think it came up on your exam too. Anyway, in this case, though, we're going to be able to trap the 1.886 between two closest values of Z stars. Would I be right that it's between 1.645 and 1.960 that are right next to each other? Is that right? Okay. So 1.645 is less than the Z value we got. And what we got is less than the 1.960. So again, look down beneath that Z star row, go down to a two-sided P row. What's the P value associated with 1.645? Okay, 0.10 or just 0.1. I'm going to put 0.10 because the other has two places in it. Somebody else, what's associated as a two-sided P with a 1.960? 0.05. Okay, is it getting low up here? Okay. So for two reasons, I've written both decimal places here, even with a 0.10. Because for comparison, which one's bigger, a dime or a nickel? 0.10 or 0.05, which one's bigger? 0.10. Remember, we have this change in direction. So doing this the long way, what we're getting at the end is a little less exact. Our probability, all we know is it's between 0.05 and 0.10, i.e. between 5% and 10%. Let me write that over here. But what is our level of alpha? Still 5%. So where is P? Even though we don't know the number this way, we just know the range that's in between it. Is P less than alpha, less than or equal to alpha, or is it bigger than it? Bigger than it. A shortcut, I would want you to write both numbers, but then a shortcut after that would be to say, well, if it's in between two values, if it's going to be bigger, then the smaller of the two things we just got from the two-sided P row would have to be at least as big as alpha. And we'll see what to do in the other direction here with our next example. Okay, so do we reject or fail to reject the null hypothesis since P is greater than alpha? P is greater than 5%. Reject the H naught or fail to reject? Fail to reject. Okay. Similar interpretation to the previous one then. The sample has not brought us enough evidence to say that the population mean mu is different from 22 micrometers per hour. If we don't have enough evidence to go that route, for now we have to stick with believing it is 22 micrometers per hour. Questions? Here's the good thing about the calculator then. All I did was change that 24 to 22. I could have changed this 24 to to 22. Rounding that to 4 places, that's about 0.05 watts. What would the rest of that be after we round? Well, I've got the 0.05, so then the 9, we have to go 4 places. 0.0593, which as a percent, that's 5.93%. That's just a more exact value for P that is between 5%, as the table C approach gives us. And we'd still draw the same conclusion. Fail to reject H0, the probability is too high. We don't have enough evidence to say that it's not 22. We're sticking with thinking it's 22, at least on the basis of this particular sample. Questions? What if biologists, just by some chance, instead of demanding in this experiment, or maybe their experiments in general, maybe they don't need 5% or less to be convinced that they should reject? What if they were willing to go with alpha equals 10%? Either way you look at it, whether you get this more exact version or something that P is in between, what if alpha was 10%? How would our p-value compare to 10%? It would be less than. Table C version didn't give us an exact number, but it says it's less than 10%. This one, specifically 5.93%, that's less than 10%. What would we do then? Exactly. Even if it's equal, we would reject. Point that for a couple seconds over here. Hopefully that will show up okay. Oh, didn't know you were going to have to do that. Alright. Just leave it there for a few seconds. The interpretation would be at the 10% level, we do, from this sample, have enough evidence to say, no, the mean is not 22 micrometers per hour. It must be something else. That would be like saying in a court, you brought enough evidence to call the defendant guilty. You've convicted. Questions? All right. Going to make another change. What if, instead of saying that we're doing a two-sided test, what would a one-sided test look like? Instead of not equal to 22, what are some possibilities of how mu compares to 22 in the alternate hypothesis? We're not going to say that it's not equal. What other comparisons could we make between mu and 22? Okay, that's one possibility. In fact, what I had in my notes was to have the other direction instead, less than. And this isn't less than or equal to or greater than or equal to. This is strictly less than. The only equal to part in your hypotheses should be talking about the null hypothesis, which you claim that mu is equal to from previous evidence or previous belief. Well, what would that one-sided test change if you're doing it the long way? Not very much. You still have to have an alpha stated in advance. If you try to do what I just did by switching from 5% to 10%, that's really cheating. It's Switching to 10%, I got something where I was failing to reject the null hypothesis before. I go, oh, well, what if I said 10% and 5 instead of 5%? Oh, well, then I get to reject it. Reject the null hypothesis. No, you state it in advance, and you stick with it. And again, different academic fields or other things outside of academics that apply statistics probably have their set percentages that they tend to go with, that you would learn about as you proceed in your studies and early in your career if you wind up applying this. It wouldn't change how we compute Z. It's the same formula. But then our comparison would change. Instead of 5% and 10% from this example, instead of looking in the two-sided P row, with that 5 and 10%, now you would be looking in a one-sided P row. So, in a one-sided P row that's above it, what two are closest? Well, we already have what's in the Z star row, what's closest to 1.886, right? Even that didn't change. Subtract down not to the 0.5 and 0.10 from two-sided P, but just go to the one-sided P. What values are we getting here? Now, I've already made the change in the directions. Like I said Friday, watch that you actually write them in the correct order. I've got less than signs, so I'm going least to greatest. It might even help to put an extra 0 after the 5 on this bigger number, so they're both going out 3 places. Number 1, to help you make the comparison, and then number 2, if you need to write it as a percent. How does that compare to alpha? Well, alpha is 5% or 0.05, which is this. This is 5% and this is 2.5%. So P is less than 5%. What do we do there? Before somebody else. If P is less than or even equal to alpha, how many say fail to reject? How many say reject? If P is less than or equal to alpha. How many say reject the null hypothesis? How many say fail to reject? Okay, we actually have it over there. What we have is a z-score that's high enough and a probability that's low enough that this is kind of odd. If it's low enough, if it's less than or equal to alpha, that's when you reject. Again, this is like before break with the author's claim that he could make 80% of his free throws. And then somebody tested him on it, said do 20 of them. He was only successful with 4. That was a binomial probability instead of the 3 conditions we needed here, one of which was normal distribution. But in any case, the probability was so darn low, either he had a really bad day, or his claim was false. It turns out we all seem to be saying, well, it's so low, it's probably not even just a bad day. Much more likely that the claim was false. That's what we're saying here. By rejecting the null hypothesis in a one-sided test at the 5% level, it would seem that there's more evidence that the mean is less than 22 micrometers per hour for the population's average healing rates. So that we're moving away from saying it's just equal to 22, but less than 22. That's the population of newts, their mean healing rate in micrometers per hour. Questions? Now, do you notice how it differed from a one-sided versus a two-sided test. We had the same things before, but in example 2, I didn't write example 2 on that, but our previous one was example 2. When it was two-sided, did we reject at the 5% level? Or did we fail to reject the null hypothesis? Failed to reject. Changing whether it's a two-sided or a one-sided test can make a difference. And really, again, that's something that should be decided in advance. You have reason to believe it's not just different, but that it's more than or less than. Without having figured out X bar, you don't even have your sample yet. Is there some other sample maybe that's suggesting that direction that you then want to go test? It should be stated in advance. And you know in advance whether you're going to do a one-sided or a two-sided test. What would it change if we were to use normal CDF instead of calculating Z and using table C? If you switch from two-sided to one-sided, what would it change in what I have up there? Yeah, we would take that out. And that's going to give us, okay, so we can round that to 4 places. In fact, I can take my previous result and just divide it by 2. So to 4 places, what would we have? Okay, so 0.0297 or 2.97%. Again, it's more exact. Table C just said it was going to be the probability, the p-value was between 2.5 and 5%, and that is. Our conclusion would be the same. Since that is less than or equal to alpha, we would reject H naught. It would be green. Yep. Okay. Now I want to talk about this more Wednesday, but the two-sided test and the fact that I was picking numbers that were in the confidence interval. Hopefully, if you look at your notes between now and Wednesday, take the first 2 examples where they were two-sided. Failed to reject on both of them. And I was picking values for mu, a claimed mu, in the null hypothesis that were in between here. Both the 24 and now the 22 are in there. What if I go back to a two-sided test and I pick something outside? It could either be up above or I could pick something that's below. Let's see here. Let's go with something above. Let's go with 30. Let's claim that mu is 30. I'm going back to a two-sided test, so the alternate hypothesis would just be mu is not 30. And again, let's keep alpha at 5%. What's the order of your subtraction? Let's see here. We'd still start with that 25.5 stuff. Subtract 30 from that, and that's still all going to be over a divided by the square root of 18. So we're first doing the long version. Find out Z. Find stuff related to that in the Z star row. And then a p-value in between from the two-sided p row. Negative 2.357. Let's see if we can confirm that. Oops. 18. So like that's what I'm getting as well. Can we get one more person to back that up? Good thing I did that. If it's negative, some of you might go, wait a minute, there's no negative Z star values in there. Well, Remember that a normal distribution curve is symmetric. So we're claiming here that mu is 30, and our x bar is below it this time, which explains why we have a negative value there. 25.5, bunches of 5s, and the 6 there. And we want to see if it's extreme enough to be in one of these tails. That would total up to, again, 5%. So, if that's a negative value, and everything about C star here is positive, use the symmetry and take its absolute value. Instead of saying, am I extreme enough to be far to the left, take the positive version of that and say, am I extreme enough to be far to the right? Which, I guess I didn't realize that could have political ramifications there. Hey, I'm a leftist extremist. Hey, I'm a rightist extremist. Must be Monday because very few of you are smiling. Anywho, so what is 2.357 in between? We're going over this way. What's in between? Okay, so what are our two-sided p's here? 0.02. Okay. And the other? Okay. What were we comparing P to? Besides this, what else do we have to compare it against? %, the alpha. By the way, I made a mistake here, deliberately. Got to change those directions. Remember, as Z is getting bigger, P is getting smaller. If you'd rather rewrite this afterwards as 0.01 less than P less than 0.02, that's fine. We say the same thing. Also, something else I would not want to see, besides not making the switch at all, is if you had them opening up like two alligator mouths towards P instead of a least to greatest left to right, or in this one, left to right, we're going smaller, smaller, smaller. Either way. This doesn't make sense then. How does P compare against alpha? Is it less than or equal to it, or greater? Okay? So in this case, if you think it's going to be less than, the bigger of these two boundaries, that is also less than it. So yes, P is less than, even if it was equal to, that would be okay. P is less than or equal to alpha. What do we do then? Reject the null hypothesis. Notice when I did that, it was a two-sided test, and 30 was outside of the confidence interval. When I did other two-sided tests, I was picking things that were inside. Look back at the notes there as to whether we rejected H0 or failed to reject when my claim mu was inside. The one-sided test, all bets are off on any comparison I'm trying to get you to think about, that we'll talk more about on Wednesday. Anyway, real quick, if you want to do this by normal CDF instead, go back to multiplying by 2, and we would have to change two things actually. All right, let's see. Since this time I have x bar less than the claimed mu, I'm not going to go from x bar to 10 to the 99. If you look at my drawing here, I'll look over on this part for a moment. Look at the shading in the tail on the left. I would go negative 10 to the 99 up to my claimed x bar. So negative 10 to the 99. And normally I would not do this, but because I'm trying to type over some stuff without using the insert key, I may not be typing enough 5s. This will still make the points. Hold on. 24 to 30, that's right. Yeah, that's giving me a number that's supposed to be a probability. And that being bigger than 1. If I change that to a percent, that'd be a probability of 159%. That couldn't be right. So think that needed to be changed to 30. There we go. And is that in between the two things we had here? Okay. So again, it's just giving you something a bit more exact. And if you learn to do this from some tutors or figure it out on your own how to use table A, it would be something similar. You're still going to have to ask yourself, when do I double or not? So that's because the previous examples had x bars bigger than the plain mu. So we wanted to know if we were far enough right to be a. Okay, that's because of the symmetry also. Okay. So these, they didn't give us another half of this, another page where we had negative z stars. So yeah, we took